Mr. Maynard, how did we come to design a spacecraft like the Lunar Module and the Apollo Command and Service Module? How did we decide to go to the moon the way we're going, in other words?
There were, of course, several concepts as to how one might go to the moon. One of the ways that you could land on the moon would be to land the entire spacecraft that you had previously been thinking of as going around the moon or into orbit around the moon. Another concept would be to leave that spacecraft in lunar orbit and with a smaller spacecraft go down and land on the moon and come back up and rendezvous. And that, of course, is the approach that we've taken. Now, the approach of landing the total spacecraft on the moon, it turns out, costs you considerable more payload at translunar insertion. The reason being that you have to land on the moon the propellant that you would use to give you the velocity increment to come from lunar orbit back to an Earth transfer orbit. One of the big weight gains in using the lunar orbit rendezvous approach that has the lunar module involved, the big weight gain there might be thought of as leaving the propellant simply in orbit that you would take to do translunar and trans-Earth insertion, then coming back up and rendezvousing with that propellant. And that would give you a considerable weight saving. Now, simply rendezvousing with the propellant is, you can't quite conceive how you would do that. But anyway, that's the kind of a weight picture that you end up with. So we very early had the concept that we would land the vehicle directly, and in order to get the payload, total payload, ability to do it with the Saturn V launch vehicle, again, which was used for the Apollo 8 mission. The concept was conceived of Earth orbit rendezvous, where you would replenish the propellants in the launch vehicle in order to inject a larger payload at translunar insertion velocities. Now, that meant you had to develop Earth orbit rendezvous and the activity associated with refueling or adding another stage to your vehicle in flight, which, of course, as you know, occupied a considerable amount of energy in the Gemini program, and could well have been done. Prior to Gemini demonstrating this, however, we reviewed the other advantages and disadvantages of Earth orbit rendezvous versus lunar orbit rendezvous. And one of the major advantages of lunar orbit rendezvous was simply this, that the spacecraft, the command module, service module portion of the current spacecraft, think of the functional and performance requirements of that, and think of it starting at the end of the mission. You have the command module sitting in the water, floating, supporting men for something like 3 days in anticipation of some problem in recovery and so forth. So we have a requirement for it to be a ship with communications and will support life in the water and not get them too seasick, although it apparently is a good seasick generator. Then you back up and you say the next requirement it has to fulfill is the safe landing. And we did look at all kinds of things, rotary wings, parachutes, landing rockets, so forth. And we finally concluded the parachutes, of course. And but the crew had to lay flat on their back for the landing in order to withstand most favorably the impact. And then we go through the entry with the heating, and we used an ablative heat shield, and that fulfilled the requirement of surviving the entry heat loads. And then it had to be the command center for the rest of the mission. And then going back, let's go back now to launch. It has to be the command center for the coming out of the atmosphere. It has to be the abort haven for the crew in case something happened to the launch vehicle behind it, so it had to withstand all kinds of dynamic problems if it were to come off the launch vehicle and tumble and so forth. And it had a launch escape. We put a launch escape system on it like Mercury had, because that was the most straightforward way and the lightest way of doing it in this particular case. The ejection seats were in fact the better way to do it in Gemini, but in Apollo the best way was with the launch escape tower. Now, when we take all of these functional performance requirements of the command module, and then we add to them the functional requirement and the performance requirement to land on the moon and have the visibility to avoid local obstacles and so forth, just think simply of how it is the crew sits. For them to take off from the Earth and land in the water, you can picture them laying on their back looking along the longitudinal axes. Landing on the moon, if they were to land, say, tail down, you'd want them sitting in an entirely different way looking out some side window. And you end up with very complicated couches and window arrangements, and display panels get they need two kind of display panels. And as soon as you add more functional and performance requirements to a particular piece of hardware, that hardware gets more complicated, to the point where you finally say, I can't. It's the straw that broke the camel's back and so forth. So we decided that we should split the functional performance requirements up to simply the business of being the haven for launch and landing and recovery and general command and spaceflight, and separating out those functions that associated with landing on the moon and lifting off from the moon and exploring the moon, the business of getting in and out of it and getting out on the lunar surface. Separating those functions into two separate pieces of hardware, and then each of them would be able to perform that function much better. The original concepts, you're right, included such concepts as a bicycle frame with minimal propulsion systems on it, minimal walkie-talkie kind of communication systems, and so forth.
And a guy in a spacesuit sitting out there in the void, maybe?
Yes, and functionally they could perform the major elements of the mission. However, the risks were very considerable, and it wasn't the kind of vehicle, those kinds of concepts weren't the sort of thing that would really develop the technology that we wanted to develop, and they certainly were risky, and we didn't want to have these kinds of problems in the program, so that the NASA had as its one of its major goals to actually make this lunar module a proper spacecraft that fulfilled its functional and performance requirements in a manner that was consistent with the kind of vehicles that we would ask people to fly in, that would be safe, and we just didn't feel that we ought to embark on this kind of an operation in any kind of a flimsy device.
The Lunar Module, one of the most complex pieces of space machinery ever designed, has a long history evolving into this bizarre-looking craft which we now expect to land on the moon. How did it come to be this way?
When the NASA decided to use the lunar orbit rendezvous approach to lunar landing, inherent in that decision was to do so with a good and proper spacecraft that fulfilled the functional performance requirements in sufficient detail so that the vehicle would be safe, reliable, and would represent the best capability that the country had to build a vehicle.
Was a concept thrown out to the aerospace industry, to the big builders of airplanes to try to play with, to come up with better designs or to interpret? How did this happen?
Yes, it was sent out to the major contractors as a request for proposals. There were 9 major contractors that had the ability really to build this vehicle within the country. The Grumman Aeronautical Engineering Corporation, who have the contract now, Republic, Martin, Lockheed, Ling-Temco Vought, Convair, Northrop, Douglas, and Boeing. They all submitted proposals that fulfilled the functional and performance requirements of the request that the NASA had submitted. They took a considerable time to deliberate on these proposals and came in, each one of the vehicles that they proposed being really quite different. Now, the proposal that the Grumman people submitted was quite different from what we see today, and the reason that it was that it has evolved from what they proposed to what we see today is, I think, the point of your question. The first thing we did after we had all the proposals in, we evaluated them, the NASA did, and we selected the contractor to negotiate with. And when we picked Grumman, all of the other contractors said, NASA, you can use our proposal and all of the engineering and technical work that we have done to really make this thing a good and proper vehicle, and any ideas we've got in those vehicles you can have. And we gave all of the proposals to Grumman, and Grumman looked through the good features and the bad features of each one of them, and worked on improving, modifying, and really basically changing an awful lot of the concept that they originally proposed. And it through this 9 contractors' proposals, we've got here essentially the good features of each incorporated into the final vehicle.
When was the lunar module, as we know it, pinned down? What year did Grumman then begin building the actual vehicle? Do you know?
It was about, it was in 1963 when Grumman started on the studies, and they studied the configuration for about a year before we committed certain pieces of hardware to this configuration. And of course, in the about 4 years, it has evolved in rather minor detail since then. Well, some things not so minor, but it's generally been configured like this for 3 to 4 years. The reason that it looks rather ungainly with respect to no aerodynamic cleanliness is that we had no requirement to make it look aerodynamically clean, and we didn't put any requirements into it that it didn't need to have, because it had enough of them. Now, it has let's first of all talk about the appendages, like the landing gear.
The spider's legs.
Yes. The reaction control system quadrants, and the antenna, the front porch that the crew gets out on to go on the lunar surface, the radar, the bays that stow equipment in the descent stage, and the access hatches and the docking tunnel at the top, and so forth. The original proposal from Grumman had 5 landing legs, and the current configuration has 4. Some of the proposals that were submitted had as many as 6 and 8 legs. The numbers of reaction control engines on each of the proposals, in fact, were different. Each one of the proposals had a different number of engines. We currently have 16 engines on the reaction control system engines. They, of course, are to control the attitude and provide the ullage just before you fire the main engines. And they, of course, have to be sticking out a long way from the center of gravity in order to take advantage of the moment arm to minimize the amount of propellant that you would use to perform a particular maneuver. So those engines get stuck away out. The landing gear legs get stuck away out in order to give stability on the lunar surface. The antenna gets stuck away out and away from these engines so that the plumes don't adversely affect the antenna. The rendezvous radar has to be away from the engines, but it does have to be close to the inertial measurement unit of the guidance system, and so forth. Now let's get to the question of tankage in the descent stage. The Grumman proposal had more tanks in it than we currently have in the descent stage. We have 4. There was a difference in the original proposals. We had a different number of tanks, different number of landing gear legs, different number of reaction control system quadrants. Now we have 4 legs, 4 tanks, 4 RCS quadrants. And when you kind of think about it, the structural arrangements now become pretty practical, where as long as you've got the same number of everything, you can package it a lot better. So that we can have the RCS engines firing between the legs rather than some of them firing between the legs and some of them firing right on top of the legs. And of course, that would give you a hard time on the legs where the engines were hitting them, and give you different control moments and so forth. And the ability to house and support the propellant tanks, now you end up using the same primary structure that you use to support your landing gear legs. Now we use the same primary structure for the landing gear legs to support the whole lunar module to the spacecraft limb adapter in the launch vehicle during launch. And now we have an opportunity to pick up on some hard points at the ascent stage to the descent stage.
All of this makes good sense looking at a model here as you describe it, when you begin to see how all these things came together. Something that occurred to me is the fact you alluded to a few moments ago, and that is that it has no requirement to be aerodynamically smooth. We don't have to see smooth, straight, or curved surfaces. The things we need to see are practical coverings and a practical arrangement of the equipment needed, and that's what's evolved then.
Yes, that's right. I think as soon as you can get away from the idea that it has to look pretty, and you have it fulfilling the functional requirements, and once you understand those functional requirements and you look at it and you say, my, doesn't it fulfill those functional requirements beautifully? And you say, it sure is a beautiful looking vehicle then.
And that's what you as an engineer are doing.
Yes, it looks very nice to me. It is very much like the P-51 Mustang fighter plane was near the end of the Second World War. It compared to the Spitfire, the Tempest, the Focke-Wulf 190 was a very angular looking airplane. And but when the operational people like myself came to understand why it is that it was built like it was built, it became a very pretty airplane, especially when it performed so well.